Today we begin our AP prep. This is a list of the topics that we are going to be covering. We're going to start with FRQ topics and then go to multiple choice topics. We begin today with area and volume. So this will be a review of area and volume. As you can see, this is a list of most recent exams that each of our topics was seen on for the FRQs, just FRQs. So for area and volume, as you can see, and I didn't go before 2005, but as you can see, it was on there a lot for a while, and then it's been skipping recently. So who knows if it'll be on this year's or not, but we will be ready for it. So I'd like to begin by just reviewing our concepts that we have with area and volume. So when we are, for area, let's say that we have two curves, F and G, and let's say that we want to find the area between them from some x equals a to x equals b. So area between them, we know that the integral of f of x gives the area under f of x. We know the integral of g of x gives the area under g of x. If we want this area between them, then we can say that the area is the integral from a to b of f of x minus g of x dx. And our expression would be very similar if we were taking it with respect to y. So if we had two curves, say f of y, f is a function of y and g is a function of y, and we were finding the area between them from, say, y equals c to y equals d, let's say that. So this would be area in between here, would be the integral from c to d of the outer curve f minus the inner curve g, because the integral of f of y would give the area from the curve f to the y-axis. So those are our two general formulas. So I think of it as the top curve minus the bottom curve, or the right curve minus the left curve, if we're in Y's. Now let's take remind ourselves about volume. So we started off when talking about volume. Let's say that that's F again, and this is G again. And let's say that now we have this region that is the base of a solid. So this region is the base of a solid. So our solid is sitting on that, and it's coming up out of the page, right? And that solid can have a variety of cross sections. Maybe they are squares, maybe they are equilateral triangles. We had several, right, that we covered when we did this back in the fall. So our most basic formula for volume that you really do need to know, volume is equal to the integral from a to b of the area function, dx or dy, it doesn't matter. So that's your most basic formula that you really do need to know. If you have a question dealing with volume, that's your go-to. All right, that will lead you in the right direction, especially in more of a confusing problem. We had one on the 2018 exam. So, all right, so that's your go-to formula for that. So it depends on, so the area here, let's just say we have squares coming up out of the page. So that's your first square coming up out of the page. And we're going to give it a little thickness, and so that it has a little volume, the thickness will be your dx. So it'll be the area function times your thickness, your dx. So that was not a good shape. Okay, anyway, I'm kind of destroying this here. If we start at A and go to B and add up all of the areas, we will get the volume. So for cross sections like this, we needed to know the area of each cross section. So the area of a square, of course, is side squared. And the side here, we called that S when we were doing it. The side is just the top minus the bottom, because that's the length of S there. If you wanted the length of this, that would be, we would take the top Y value minus the bottom Y value. So S is going to be the top curve minus the bottom curve each time. Unless you're this would be perpendicular to the x-axis. If you're perpendicular to the y-axis, then our S would be the right curve minus the left curve. Everything else is the same. So area of a square is side squared. Area of an equilateral triangle. Equilateral triangle is square root of 3 over 4 times S squared. The area of a semicircle with in terms of S, is pi over 8 S squared. And if you want to see the development of those, go back to the other video, go back to the other notes back in the fall. I'm just quickly reviewing these. The area of an isosceles right triangle with a leg on the base. So leg on the base is your 1/2 base times height, so 1/2 S squared. If you have an isosceles right triangle and the hypotenuse is on the base, it's half of that, so 1/4 S squared. What if they give you a different cross section and they describe it somehow so that you don't have one of these handy little formulas? That was like they did on 2018. If they don't give you one of these shapes, you have to revert to this, and that will guide you. Okay? Integral of the area is volume. Remember that. All right. What if we have our region from A to B, and this is not the base of a solid. This region is being revolved around a horizontal axis. If this region is being revolved around a horizontal axis, that will also form a solid. Let's see if we can draw this. Let's say that we're revolving. I don't want to revolve it around the x-axis just because it won't always be the x-axis. Let's say we're revolving it around y equals c. So there's our axis of revolution, and we're revolving this around. So this side will be flipped over here like that. Maybe it'll look something like that. And this will go up here, so it'll look something like that. So this is coming around, and this is coming around. This is going behind the page. This is going behind the page. Like that. So we have this solid. Okay, and it has a hole in the middle, right? So if you're talking about cross sections, because remember, this is our go-to for volume. That's our go-to. So we want the area of a cross section, just like we had an area of a cross section up here. We want the area of a cross section. Well, this time the area of a cross section is a circle with a circle cut out. So the area of a circle is pi r squared, right? So we are going to have, for each area here, we're going to have a big circle minus a little circle. So we called that big circle area pi times big R squared, and we called the little circle's area pi times little r squared. That's how we did it back then. So big R will always be your top curve, in our case f of x, minus the center, and little r will be the little curve minus your center. And then your volume of that resulting solid would be the integral from a to b of pi times your big R squared minus pi times your small r squared, your inside. Outer radius, inner radius. That's it. That's all there is to it. So let's take a look at your problems that I printed out. And I know I'm going to be updating this each year, but this year that I'm making it, it's number 2. But again, I'm going to be changing this. As we get more problems, I always update my sheet. So this is the problem from 2011, and I'd like to start there. This question was with no calculator, so we will not use a calculator. Let me remind you on here, some of these are with a calculator and some are without. Remember, for us, numbers 1 and 2 are with a calculator, and the rest 3 through 6 are without. So it just varies from year to year. So we're going to do this without a calculator, which means, yes, you're going to have to integrate. So keep that in mind. Okay, we have f is equal to e to the 2x. R is the region in the first quadrant bounded by the graph of f, the axes, and the vertical line x equals k, where k is positive. So if that confuses you, make k a number in your head and ask yourself what you would do with that, because it's the same thing. So here's our region. Obviously, here's the curve. Here's x equals k. And in part A, we want to write but not evaluate an expression involving an integral that gives the perimeter of R. So write but do not evaluate. That gives the perimeter of R in terms of k. So the perimeter means we're adding up all of these sides of this shape. So the straight lines are not going to be a problem. The curve is the more interesting part of this. So for that one, we need the length of a curve. So we go to our pocketbook, our toolbox, and pull out our formula that gives us the length of a curve. The length of a curve is the integral from a to b. Our a is 0, our b is k, so from 0 to k, that's the leftmost x and the rightmost x. And then this formula came from the Pythagorean theorem. Square root 1 plus the derivative squared. The derivative squared. Well, the derivative of f here, the derivative is 2e to the 2x. So this will be 2e to the 2x squared dx. So that integral gives you the length of this curve. And then we're going to add to that the other sides. Well, this length is 1. This length is k. This length is the top y minus the bottom y. So the top y is e to the 2k. Oops, 2k minus 0. So this expression gives the perimeter of R. Let's go on to part B. In part B, region R is rotated about the x-axis to form a solid. So here's our axis of revolution, and we're revolving this around. So it's going to look kind of like that. Okay. So find the volume of V, find the volume V of the solid in terms of K. So I go to my general form for volume is the integral of the area, right? The area function. So the integral from the leftmost x to the rightmost x of the area of a cross section. Well, here there is no hole in the middle because the axis of revolution lies right, the region lies right on the axis of revolution. So there's no hole. A cross section is just pi r squared, right? So the cross section is just pi times the radius squared. Well, the radius is always just the curve minus the 0. So it's just the curve. squared. So pi r squared, right? Now it says to find the volume. Not just write, but don't evaluate. Find. So we actually have to integrate this. So I think I'm going to take out this pi. And then we will have e to the 4x, because a power to a power, you multiply those powers. And now we're going to go ahead and integrate. So this will be pi times 1/4 e to the 4x. We got very good at integrating e to a power like this when we were doing by parts integration. Integrated from 0 to k. I think I'm going to go ahead and move that 1/4 outside. And then I'll have e to the 4k minus e to the 0. That would be a safe stop spot. I always advise you to safe stop. So I will safe stop there. If you just can't stand it and you have to go forward, make that e to the 4k, pi over 4 times e to the 4k minus 1. We could also distribute the pi over 4 through, but why? All right, in part C, the volume V found in part B changes as k changes. Well, that's true, because if k got bigger, the volume would get bigger. If k got smaller, the volume would get smaller. That makes sense. If dk dt is 1/3, determine dv dt when k equals 1/2. All right, as soon as you see something like this, it throws you into a related rates problem, because now we need to get time involved. This is not bad. We found the volume right here. We found the volume right here. V is equal to pi over 4 times e to the, gosh, I keep putting that k first, minus 1. That's the volume. If we want to get dt involved, all we have to do is take the derivative of both sides with respect to t. Related rates is not hard, you guys. Not hard. We're going to have dv dt is equal to, all right, if we distribute this pi over 4 through, the last term is just going to be a constant, and the derivative of a constant is 0. And now we have pi over 4 times e to the 4k, and the derivative of that is pi over 4 times 4e to the 4k. That would be, we took the derivative with respect to k. Now we need to take the derivative with respect to t, so this is times dk dt. Little chain rule in there. That's using the chain rule. Or you can call it implicit differentiation, which is the chain rule. Okay? So, that would be fine to leave it in this form. Of course, we can cancel out those 4's. And now, when k is 1/2, dv dt is, I am going to cancel out those 4's now just because I don't want to write it again. Pi e to the 4 times 1/2, because k is 1/2, times dk dt, which is 1/3. And that would be a safe stop spot right there, so I'm going to safe stop. And that's it. Let's take a look at how they scored this back in 2011. For part A here, this was worth a total of 3 points. See how they broke it down. 1 point was for finding the correct f prime, for using f prime here. 1 point was for the integral, the entire integral. And 1 point was for your answer, the entire answer. For the part B, this was worth a total of 4 points. Let's see how they broke that down. 1 point for the integrand. The integrand is the inside of the integral. So the integrand here. Don't forget your dx's. 1 point for your limits. The limits of integration. 1 point for the antiderivative. Here was our antiderivative. and then 1 point for the answer. So that means every FRQ is worth 9 points. That means this last one was worth, this last part was worth 2. 1 point for applies the chain rule. And 1 point for the answer. And that was 2011. Now let's go take a look at number, well, it's my number 4, but again, that's going to change as we go through, as I change this, update it each year. But this was the one from 2008. And this one was with a calculator. So I'm going to grab my calculator. Y'all grab your calculator. We have got, that says let R be the region bounded by the graphs of y is equal to sine of pi x and y is equal to x cubed minus 4x. Which is which here? Which is which? If you are unsure, very quickly go plug those into your calculator. But to me it's pretty obvious that this is the sine wave, and that means this one must be a part of x cubed minus 4x. So there's y is equal to sine of pi x, and here is y is equal to x cubed minus 4x. Part A, find the area of R. Not a problem for us. Integral 0 to 2 of the top curve minus the bottom curve. Top curve minus the bottom curve. So sine of pi x minus x cubed minus 4x. Be sure to use parentheses for this x cubed minus 4x, or distribute the minus through. And now we go to our calculator, plug that into our calculator. Since this is an FRQ, it has multi-parts, I know I'm going to be using these two equations multiple times, so I'm going to go ahead and put those in. So always do that. It'll save you time, which is precious for this exam. So I have both of those in, and now I'm going to go to my home screen and do this integral. Math 9, 0 to 2, our top curve minus our bottom curve. And we get a nice, neat little 4. Okay, that part, you guys, was worth 3 points. 1 point for the limits of integration, 1 point for the integrand. That includes the dx. Make sure you have your dx. And then 1 point for the answer. Part B. The horizontal line y equals -2, y equals -2, splits the region into two parts. So yes, it would. Y equals -2. Y equals -2. Remember, that's horizontal. It splits this region into two parts. They're not equal parts, but they are two parts. Write but do not evaluate. Write but don't evaluate. An integral expression for the area of the part of R that is below the horizontal line. Below that horizontal line. So we want this area. That's not a problem for us. We know the integrand is going to be just the top minus the bottom. The top is y equals -2. The bottom is our y equals x cubed minus 4x. So I know we're going to have -2 minus x cubed minus 4x dx. The question is, what boundaries do we use? We certainly are not going to use the 0 to 2 anymore. We need to find these intersection points, right? These intersection points are where y equals -2 meets y equals x cubed minus 4x. So I go back to my calculator. I need to get -2 involved, and I do not want to see this top curve, so remember, you can go up there, press enter on the equal sign, and now you won't see that as it graphs. I think for my window, I'm going to use a window similar to what they have here. So for my x's, I'm going to go from a little bit to the left to a little bit to the right of, I think I'm just going to go to 2. It looks like that's all they went to. And then for my y's, a little bit, maybe -3 will work there. And then up to like 1.2, something like that. Okay, that's perfect. So I could have gone below -3, but that's okay. So second calc intersect, enter, enter, enter will give us that leftmost intersection point. I am telling AP what I did. I'd never ever just throw in a number on the paper. Do not just come and put your numbers here without saying where they came from. So I'm going to tell AP that y equals -2 intersects y equals x cubed minus 4x at x equals 0.539 and x equals, now I don't want to go find the other intersection point quite yet, because if I do, I'm going to lose that value, and I don't want to lose that value. So I'm going to go to my home screen, store that x value in for A, or some letter. And you know what? I'm going to tell AP I'm doing that. That way I can just use A over there on my integral. Now let's go find the other intersection point. Get a little closer over there. 1.675, and I'm going to store that in for B. So go to my home screen, store that x value in for B, so we're not losing those. And then over here on my integral, I can just put from A to B. And I didn't leave myself much room here. You are going to have plenty of room on the AP exam, plenty of room. So don't worry about trying to squeeze the things in. I just try to save paper, so I don't do a whole lot. I don't give you a whole lot of space. Math 9, A to B of -2 minus, and this was our y2, right? And we get 0.9 point, okay, that's not right. What did I do wrong here, guys? What did I do wrong? Oh, I didn't do anything wrong. I didn't do anything wrong. I just didn't have to I didn't have to evaluate it. Okay, so we don't have to evaluate that. Okay, let's make sure we read the directions very carefully. Right, but don't evaluate. Okay, so that's it for part B. This part was worth 2 points. 1 point for the integrand, and one point for the integrand, and 1 point for the answer. That's how they scored that. Okay, part C. Now the region R is the base of a solid. And for this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of that solid. So we're back to the whole region R, and this time we have to find. So we actually will put it into our calculator this time. So find the volume of the solid. So here's my thought. Volume is the integral of area. And in this case, each cross-section is a square coming up out of that page, right? So my volume will be the integral, we're back to from 0 to 2, the integral of the area here is side squared. And the side is just my top curve minus my bottom curve. So that would be my sine of pi x minus the x cubed minus 4x, and we square that because that's the area of a square. Side squared dx. That goes into our calculator now. All right, integral 0 to 2. I'm squaring, so the top curve minus the bottom curve squared dx. Okay, there's that 9.978. We give at least 3 decimals. At least 3. You can truncate or round that last decimal place, but at least 3. That was worth 2 points. 1 point for the integrand again, and 1 point for the answer. Lastly, in Part D, Region R models the surface of a small pond. At all points in R, at a distance x from the y-axis, the depth of the water is given by this. So they're giving us the depth of the water. Find the volume of water in the pond. Okay, this is one of those times where we need to revert to what we know volume is. In my mind, I know, I'm telling myself this. I'm not writing this for AP, I'm just telling myself this. Volume is the integral of the area function, dx or dy. So, they give me the depth, and we're at a distance x units from the y-axis. So, this is x units from the y-axis right here. And so, right here, the depth is given to me. So we're going underneath the page. The depth will be right there. So I have a rectangle. So my area will be the area of a rectangle. The length of the rectangle is the top minus the bottom again. Sine of pi x minus x cubed minus 4x. The depth is 3 minus x. So my volume will be the integral from 0 to 2. The top curve minus the bottom curve, that's my length of the rectangle, times the depth. Length times width for a rectangle. Did we have to find this? Yes, we had to find it. So we're actually going to put this into our calculator. Math 9, 0 to 2. Okay, top curve minus the bottom curve times 3 minus x dx. We get 8.3. You can either write 8.369 or you can write 8.370, either one. Do not write them both, just write one of them. But AP accepts either one. If you're ever in doubt, write what's on your calculator. Okay? But you need at least 3 decimal places. This was worth 2 points as well. 1 point for the integrand, 1 point for the answer. Now let's go to number 6. Number 6 was also with a calculator, and this was back from 2006. If you have a future year where I've changed the numbers. This one's worth a calculator. Let R be the shaded region bounded by the graph of y equals natural log x and the line y equals x minus 2. Here it's clear which is which. First of all, we want to find the area of R. Area of R. So area is always the top minus the bottom. So I know this is going to be the integral of the top curve minus the bottom curve. The top curve is natural log x. The bottom curve is x minus 2. Be sure you use parentheses around the x minus 2. dx. Now all we need is our boundaries. Our boundaries are not given to us, so we need to go find them. So back to our calculator. Clear this stuff out. In the top, for the top equation, I'm putting my natural log. For the bottom equation, I'm putting my line. And I think I'm just going to zoom for this because they didn't give us anything here. That's good. I can see this. It's not this. It's smaller than what they gave me, but that's okay. I can still see everything. certainly enough to get my intersection points. So again, I'm telling AP what I'm doing, and I'm going to say y equals natural log x intersects y equals x minus 2 at x equals 0.158 dot dot dot, and I am going to store that in for A. Now, question. Do you think we will, well, I just lost it anyway. Do you think we're going to need that y value? We may or may not, okay? If you think we're going to need it, write it down. If not, you can risk it. Let's see if I can copy that. I'm going to store that in for C, just in case we end up needing it. So I'm pulling out y and I'm storing that in C. There it is. Back to my getting our other intersection point. And x equals 3.146 dot dot dot. I'm going to store that in for B. Y equals 1.146 dot dot dot. I'm going to store that in for D. So the current x value I'm storing in for B. The current y value I'm storing in for D, so that I won't lose any of those. So this area of R, the way I've set it up, will be the integral from A to B of that. We actually have to find it, so to our home screen, integral A to B, the top curve minus the bottom curve, dx. 1.949. Let's see, that was worth, let me see what that was worth. That was worth 3 points that year. 1 point for the integrand, 1 point for the limits, 1 point for the answer. Part B. Find the volume of the solid generated when R is rotated about the horizontal line y equals -3. Y equals -3. Well, this C value was -1.8, so -3 is going to be way down here somewhere. I'm just going to draw it there. So there's y equals -3. And we want the volume of the solid generated when R is revolved around that. So it's coming around that, right? We're going to have a huge hole in this, in the middle here, right? So each cross section, remember volume is integral of area. Each cross section will be a big circle minus a little circle. The big circle is going to have the radius of this natural log x minus our -3. So our outer radius is our natural log x minus a -3. Our inner radius will be the line minus a -3. And so our volume will be the integral, still going from A to B, of pi times our outer radius squared minus pi times our inner radius squared. We actually find it, so I'm going to plug all this into my calculator carefully. So math 9, A to B, pi times our natural log squared, don't forget to square, minus pi times x plus 1 squared. 34.199 or 34.198, either one. I always like to round. This was worth 3 points as well. 2 points for the integrand, 1 point for the limits, constant, and answer. So that's how they scored it that year. Part C. Write but don't evaluate. Let's see if I can remember that this time. Write but don't evaluate an integral expression that can be used to find the volume of the solid generated when R is rotated about the y-axis. Now we're taking this and rotating it about the y-axis. There are 2 ways to do this. We can do it with the same disc and washer method that we used here, or we can use the cylindrical shell method. Okay? I think I'm going to do it both ways for you and then let you see. So if we're going to use the same method we used here, which is called the disc and washer method, if we're going to use that, then I need to get everything in terms of y's instead of in x's. So, and I do that because if I'm revolving this around the y-axis now, my outer radius is going to be here, and my inner radius is going to be here. So we're going perpendicular to the y-axis this time. And if you're perpendicular to the y-axis, you need a dy. Those are little slivers of y's. So it's a delta y here. Each of these is a little delta y. So the outer radius we need, we have y is equal to x minus 2, but we need that in terms of y. So just solve that for x. It's not hard. So our outer radius is y plus 2 minus 0. And then our inner radius will be the curve minus 0. Well, the curve was y is equal to ln of x. We have to solve that for x, e to both sides. X is equal to e to the y. So our inner radius is going to be e to the y minus 0. So our volume will be the integral. Now we need y boundaries here. So this is where we can pull out our y's that we got up here. So we're going from C to D of pi times our outer radius squared minus pi times our inner radius squared, dy. We did not have to evaluate. I almost grabbed my calculator, but we didn't have to evaluate it. So that would be our answer for that one. Okay. The other way to do this is with the cylindrical shell method. And since I've kind of butchered up that picture, let me just redraw this up here. Here's our region, and we are revolving it around the y-axis. So it's going to look like this, right? What we do with the cylindrical shell method is we still take a vertical slice. We still take a vertical slice here. And we just revolve that vertical slice around. And we get a cylinder. When we revolve that slice around the axis of revolution, we get this cylindrical shell. That's why it's called the cylindrical shell method. Okay? And we can get the area of that cylindrical shell. The area of the cylindrical shell is 2 pi RH. R is that distance, which is always, it's changing depending on where our slice is. It's changing. That's our x value. And our height is the top minus the bottom. So the radius is x here. The height is the top minus the bottom, natural log x minus 2. So the volume will be the integral. We're still using x's because we took this vertical slice, it's still a dx. So we're going back to a and b, 2 pi r h dx. So either one of those are fine. For AP, they don't require us to teach the cylindrical shell method. So every one of these will be able to be solved using the disc and washer method. So they both yield the same resulting value. Okay, that is it for our examples. So now you need to go and work the remainder of those problems in your packet.